Hi, welcome to Concept Based. I'm John Hepworth, and this one's for Year 11 Extension students that are doing polynomials, in particular doing sums and products of roots. In this question, we've got a polynomial that is degree 3, a cubic, but I just want to make you aware, first of all, that in your syllabus, this topic extends to quartics. And that hasn't happened before. Now, I know having it not happen before doesn't affect you, because this is not your syllabus, but it's new that quartics are out there. And they're quite complex calculations you have to do in the quartics. So if you are in this topic and you're looking at this video to try and just get a bit of a helping hand on how to do this, once you've got a grasp of how to do it, do extend into those quartic questions because they are now in the syllabus. But let's look at this one and see what we've got here today. A polynomial p of x has roots alpha, beta, gamma. Find the monic polynomial whose roots are 1 on alpha, 1 on beta, 1 on gamma, if this is the polynomial that's given. Okay, so first of all, there's some rules. Now, you know I don't like rules, I like concepts, right? But there are some rules. There are some rules that we know what the product of the pairs and the the sum of all of the roots are. Now, hence why it's called sums and products of roots. Now, what I want to do is make sure that you have a little bit of conceptual understanding of y is what it is. So back up in this polynomial p of x, the coefficient in front of the leading term we call a, so therefore we've got a b, a c, and a d here. Now, if we were to express this polynomial in the form of its roots, then we would actually express it as x minus alpha, x minus beta, x minus gamma. Now, obviously the leading coefficient is 2, so there would be a 2 out the front here. But look at what happens here. This alpha, if we were to expand it to go back to this polynomial, let's think of the last term. The very last term that has no x's in it would be negative alpha times negative beta times negative gamma. Negative times negative times negative is a negative. So that would actually be here at d, but it would be a negative of d. And you'll notice that this 2 is not in it because that's the a that's out the front. So it would actually be smaller than that. It would be negative d on a. That probably could move up a little bit so that you can read that. Negative d on a. And so I'm just explaining to you why the product of the roots is negative d on a. If you want to understand why the next group happened and then the last group happened, you can go and expand that whole thing out and match up the terms. But once you've done that a couple of times and you understand the concept of where these come from, you then probably can start remembering a little bit of a rule. I don't like remembering rules, but they are fast. And the rule is that I start with the sums of them because it goes to the b term. And I also take into consideration that the first one's negative, the next one's positive, the next one's negative. If you had a quartic, the next one would be positive. And so this negative second term is the b value, and they're all just divided by a. So the sums end up being negative b over a. The next term is the pairs, which is positive, right? Positive c on a. And as you saw from my expansion, the last one's negative. So the product of the roots is negative d on a. So these roots, these sums and products of roots actually have values in this polynomial. So we can find out what they actually are equal to. So here, alpha, beta, gamma is negative d on a. So negative of negative 3 is 3 on 2 is 3 on 2. C on A is 5 on 2. And negative B on A is 7 on 2. And so we have values for these combinations, these sums and products of roots. But look at what we're trying to find. We're trying to find a polynomial that has the roots 1 on alpha, 1 on beta, and 1 on gamma. Okay, well, let's go and add those roots together. So if we added those roots together, 1 on alpha plus 1 on beta plus 1 on gamma, look at what we've got. It's a bit of a nightmare because none of that relates to any of these three. These are different to what we've got down here. But if we put these fractions together, so we're going to cross multiply common denominator, we're going to get beta gamma plus alpha gamma plus alpha beta all over, I say beta or beta, I'm not sure which one is Australian English, but I'll just keep switching between the two, so I mean the same thing. So here we have alpha beta gamma on the base. Now these parts, once we put these fractions together, these now match up. Look at that. We've got this sums part. Oh, I don't want a straight line, but thank you. We've got this sums part here, right? That is our second part, the sums of the pairs. So we are going to make a substitution for that part and say that that part is equal to 5 on 2. And look at the bottom of the fraction. We've got the product, the alpha, beta, gamma, which up the top is 3 on 2. So it's 5 on 2 divided by 3 on 2, flip and multiply, cancel out the 2's, and we get 5 on 3. So we've now found what the value of the sums of the roots are in the new polynomial that we're trying to build. So the new polynomial that we're trying to build, the sums of the roots is the second term. And we actually know the first term as well, because look, it says find a monic polynomial. So what I'm actually doing here is I'm starting to build this new polynomial. I'm going to call it g of x. It's monic, so it's x cubed. And now it's got this 5 on 3 for the sums part. But remember, it's negative b on a. So when we bring this one in, this one has to come in as a negative. So negative 5 on 3x squared. And I now just need to go and find these other bits to fill in at the back here. How do I find those other bits to fill in at the back? Well, we go and do the other thing, which is a multiple of the pairs. So 1 on alpha gamma plus 1 on alpha beta. So I'm multiplying these two fractions together. 1 times 1 at the top is 1. And beta gamma. There we go. So now I've multiplied two pairs of the roots together, and we end up with this, which again, we can cross multiply. Now, when you cross multiply, this one's a little bit different because they've all got terms in the base. We don't need to put extra bits up there. We don't have to put all of the bits up there. So this first one, 1 on alpha beta, 1 on alpha gamma, just needs a beta in it. So we're just going to say beta. The second one needs an alpha in it, and the last one needs, the second one needs a gamma in it, and the last one needs an alpha in it. And now down the bottom, because we only multiplied what we needed to up the top there, we've got alpha, beta, gamma in all of them. And look, this is one of the ones that we know. We have the sum of alpha, beta, gamma up here, 7 on 2. And we know that the product alpha, beta, gamma from our previous one that we just did is 3 on 2. And again, we can now go and flip and multiply, cancel the 2's and get 7 on 3. And so that can go up into the next spot on our polynomial. Now this is the positive section. So we've got a positive 7 on 3. So we're going to keep it positive, 7 on 3x. And then the very last one, see, could you imagine doing this for a quartic? This is for a cubic. You're going to have to do this for a quartic. And so now the very last expression is just the product of all of them, which ends up being 1 on alpha times 1 on beta times 1 on gamma is 1 on alpha, beta, gamma. Now we know what alpha, beta, and gamma is because we've had that all along. So it's 1 over 3 on 2. Again, we're going to flip and multiply and we get 2 on 3. And we're going to take that up and put that at the end. Now this is the negative one again. Negative, positive, negative, negative. Did I say 3 on 2? I had 2 on 3. Negative 2 on 3. And we've found ourselves a monic, right? It's leading term of 1, monic polynomial whose roots or zeros are at 1 on alpha, 1 on beta, and 1 on gamma. Now, I did say that I have solved this a different way completely. I think I said it at the start of this, elsewhere on my Instagram, on my TikTok, and on my Facebook. So if you want to see a completely different way of solving this, go and check those out. Also concept-based. I'm sure if you type that in, you'll find me. But yeah, this is a lot of sort of equations with substitutions happening. And again, it's cubics. So definitely practice a quartic and make sure you don't get lost in this incredibly long process. But there we have it. We found ourselves a polynomial with the roots that we were after.